Since the derivative is defined at a point, if we change the point of interest, we have to redo the entire calculation. And if you've ever redone that calculation, you've seen that it's exactly the same set of steps, but with slightly different numbers. For that reason and many more, we thus want to talk about the derivative function. The derivative function f prime is a function whose domain is the set of points where f is differentiable, and whose output is the value of the derivative of f at x. In practice, the way that we'll compute the derivative function is nothing new. We'll still use the limit definition of the derivative, but this time instead of substituting a particular value, we'll leave x as being arbitrary. So for example, if we take a look at the function f of x equals 2x squared minus 4 and apply the limit definition of the derivative for an arbitrary x, we get the following. Again, the only difference between this and what we've done previously is that we have an x here instead of a number. We know what f is, so let's plug that in. And here it's worth pointing out why these examples are often a little bit more difficult than working with particular points. See that f of x term there, the 2x squared minus 4? If we were evaluating this at, say, x equals 3, it would simplify to the number 14. That's it, no variables. But in this example, we have to leave it in general. Now at this point, it's mostly just algebra. We're going to expand the numerator and do as much canceling as possible. As before, we need the h in the denominator to disappear, and conveniently, everything in the numerator without an h cancels each other out. So let's look at this. We now have a function that returns the value of the derivative of f at any point. So if we wanted the derivative at, say, x equals 3, we would compute f prime of 3 equals 12. Or say at x equals negative 2. No need to redo the computation. The answer is negative 8. Now, as I mentioned above, this calculation is generally a little bit harder than computing the derivative at an individual or particular point. However, the benefit is that we only need to do this calculation once, and then we can evaluate the derivative just by evaluating a function. Okay, let's do a harder example. Let's look at the function f of x equals 1 over root x and find its derivative function, assuming, of course, that x is positive. Before evaluating the limit, I know that there's going to be a lot of algebra involved, so I want to tackle some of that first. The difference quotient is as follows. And summing in f of x equals 1 over root x gives us this. To avoid that double fraction, let's rewrite it like so. And with cross multiplication, we get this result. Now this still isn't in a good form, since plugging h into this gives us 0 over 0, which is nonsense. So as usual when there are square roots involved, let's multiply by the conjugate. Expanding out that numerator, we get a nice expression which will lead to lots of cancellation. It leaves a negative h in the numerator, which will cancel an h in the denominator, and this leaves us with something that we can plug h into. So now we can go back to the limit. The derivative of f at x is thus the limit as h goes to 0 of our usual difference quotient, which we've simplified as above. And if we just plug h equals 0 into this, we get 1 over x times 2 times the square root of x, or we could write that as 1 over 2x root x. So the derivative function is a little bit more complicated to compute, but has the potential to save us a lot of time.